Oh, 6.
Okay.
I didn't know how to spell it, so I didn't know
No
call her bar now.
All right. First,
Hold up.
we're going to be talking about the logarithms and natural logarithms still today. There's something we need to cover, and is when we use exponential form versus just continual growth. So there's going to be two things we have to cover. But we're going to talk about logarithms, and natural logs. Okay, now we're gonna try to do an example of each of those types. Next, I want to talk about whether it's continual growth or if it's annual growth. Because this is something that I really haven't stressed, because the answers are pretty much almost identical, and I want to make sure you guys get to see like the difference between these. Once we're through that, then my goal is to finish with a few examples of what the homework will look like. So we'll get to a couple examples. I'm not going to get to homework today as long as you guys pay attention.
Is continued annual kind of like the like every year?
No.
But annuals only come out for 1 year.
Where are you getting that?
Our core plans?
Yeah, so we had to take a class by which is like,
If you didn't harvest them, they come back. So they're like, no,
But
not listening.
they have to be really seen. Most farmers don't like that. Okay. Hey, first, let's talk about logarithms versus natural when you use one or the other. So, first example, this is one that I showed you last week. Well, let's go 4 to the x, and let's change it into a 20. 4 to the x into a 20. On this particular problem, there's 2 ways to attempt this. You would not need a natural log. Now, the reason why I would not use a natural log, we're not using the natural number e. We're using a 4. But on this particular problem, there's 2 ways to do it. You could do quote-unquote circle method. Okay. Circle method is when you do this. Take 4 to the x, you have the 20 over here. You're going to loop around and equal the power. Anytime you do a logarithm, it will equal the power. So I know that my answer will have an x on this side. But over here, this is going to be log of base 4, because the 4 is actually the base, of 20 is equal to the power. That's called the circle method. You could type that in. Now, how I want you to type this in your calculator, because some people don't have the luxury of typing in the base number, you have to type it like this. Log of 20 divided by log of 4. That's right. Okay? We have to do that.
wait, hold up.
I want to see this typed in. I'm going to walk around the room to see that everyone's getting the right answer.
Come on. Wait, did you get 2? 0.16? No, I got 2 exactly.
Well, that is wrong.
I haven't used this calculator yet this year.
Okay. I was like, I got 105.
Justin, so next with ACT also had the
Type in hello, which is upside down.
Yeah, I got 6.
Why have we pretend this?
You guys got it?
Yeah. How'd you do that?
Is this right?
What I do wrong?
I got a little bit
You gotta hit the log button. Yes. How about that? Taking 20 divided by 5. Yes.
Wait, how'd you do the 5 thing?
Did I get it?
I hit 5.
How is that not right?
Did I check your reserve?
How do you do that? That's so cool.
Unless you said mine was wrong, I did the sign of 6 and radio.
Alright, good. Everyone's got it. Alright, hey, shh. Next. Now, the second way to do that problem. If you didn't like that whole circle method, 4 to the x equals 20. You could do it this way. You could take this number and you could take the log of both sides, and this is where it's going to require that you understand the properties of logarithms. So, the basic property of a logarithm, you can drop the power out front. You drop the power out front, and you have the log 20 over here. and you would simply divide the log 4 over, it will give you the same
That's
answer.
the same thing.
It's the same concept, it's just, it takes less steps just knowing the circle method and being able to write it down and just immediately type it. But some people don't like to set it up or they don't remember how, like which number goes where. So by taking the log of both sides, it will still work. Okay, now, the other example I want to talk about is a problem like this.
16.
Okay. We know it's going to be a small number, right? It's not going to be a perfect number. 8 to the first power is 8. 8 to the second power is 64. It's not a clean number. I want to show you how you can do this problem without a calculator.
You can do with the 2 to the whatever.
Yeah. 2. So,
And then you'll say
2. We stop talking.
Yeah.
Okay. What we're going to do is we're going to change the 8 to be 2 to the third power. 2 to the third with an x on it. Because 2 to the third means 8. The 16 is 2 to the fourth power. And since they have the same bases,
They can cancel.
the bases basically cancel out, and what you're left with is just the powers. So,
3x equals 4.
so if you cancel out the bases, the powers have to be equal because the bases were the same number. So to solve for x, you just divide the 3 over, and your answer on a calculator should be 1.3 repeating, because that's 4/3. Now, if you're going to do it by the circle method or the logarithmic form, you take the log of both sides, divide, you'd actually have log of 16 divided by log 8.
I did that, I got the same answer.
Yep. It's 1.3. It's just, sometimes it's nice when the numbers are clean and you know what the bases are, like the numbers are smaller. It's kind of nice to check that. Now, the only reason why I didn't do it over here is because 20 isn't a nice power. It's not like 2 to something or 3 to something. That's why I kind of avoided it. I couldn't make the bases the same, so I just avoided it and I just typed it in. So, if the numbers are bigger, I would just do logarithms all day. But sometimes you don't need to. It's pretty much, the reason I tell you that is that if you ever have to take a math entrance exam into a college, because you already had the ACDs taken, you already had the other stuff taken, but when you walk into like a university, they might have you take a math placement test. I remember at Iowa State, they didn't allow you to use calculators.
What math
So,
were you placed into?
Calc 3. Calc 3.
What? Wait, did you have to take Calc 2?
I still took Calc 2 because I only had taken Calc 1 in high school. But the stuff we covered in high school covered differentiation and it covered integrals, which is what we covered this year. So I was already past out Calc 2. But I still took it because it's still
there's
hard
literally
for
an I don't know button.
other things how to do it.
What did you struggle with Calc 3?
Oh yeah, I mean it's still hard.
How deep can math, how far can you go into Calc before you run out of Calc?
What?
Advanced calculus is like Calc 4, but then they just change names like differential equations, and then they go with abstract algebra, and then they go geometry.
So you can
We
just
have to as math. You have to take 53 credits.
Math? How many credits were you like 90?
No, I took 56 in that.
Oh.
Only one extra class? I'm kind of disappointed.
It's kind of a
We
cool
should
one.
go back to, what was your extra class?
It was math for elementary ed, and the only reason I took it is just because it showed like practical uses for like math for like projects, and I was like, okay, that sounds cool.
Did they actually teach you how to teach math, or did they just teach you math?
Not at all. They just teach you. They don't teach you how to teach.
Really?
No.
So, wait,
So
so you could go from, in one day, you could go from your advanced calculus class to your elementary math class?
And
Is
then
that not the same level?
well, the kids that were taking the elementary math were like teachers that were going to the elementary, so they just had to know how to add and stuff. But they're doing projects. Well, if you had like advanced math background, class is just kind of easy. But
I think
you
that
could
class
apply like
should be easy.
crazy concepts to what we did. So we did some fun stuff.
Like what? Like, if you put a log on 4 plus 4.
It was something like they just gave you a story out of a Sherlock Holmes novel and said prove it with math. And so we did something where you had to prove like a certain killer was like had to be this tall because of his stride that he took. Like we measured feet and we put that as a project. And it was kind of a fun class. We had
Because in elementary they only use addition or subtraction.
yeah, so we talked about that. So like how many strides did he take? How far would it be to the house and all that type of thing. They adapted it for like high school and college, like the upper level kids, because they knew they were all mixed together. So we had a weird class too, because the kids that were taking it probably should have been taking it like me and stuff. But we just thought it was fun to learn how to do a project and apply it. So it was fun.
That was fun?
It was fun. It was nice. It was kind of nice to take a breather from all the heavy stuff.
I don't really know what Calc 4 teaches
Alright.
elementary math. How many math tests have you taken every day?
Alright, hey, okay. Last thing we need to cover here is natural logarithms. We haven't done that before we get into this other stuff. Natural log is anytime you're gonna do the same concept, but it's for the natural number e. So e to the x is equal to, I don't know, let's go with 7. Let's go 7. So, if we're gonna type this in, you could do circle method. Natural log of 7 equals x. If you're gonna go the circle method. Now, the reason why I write that, the natural log by writing that, it means this. Log base e, so e is the base of 7 equals the power. You're always equaling the power. But if you don't like that, you can take the log of both sides. Log of 7. This x can drop out front. You can just have the log of e.
What?
The log of 7, and you could divide this over.
So it's e.
So log of 7 divided by log of e. But again, why this turns out to be the same thing is that in a change of base formula, you could bring this up as the base, and which is the natural log. So you can eventually change those, but if you actually divide this, it'll actually turn out to be the same number, whatever that is.
1.945.
Questions? Alright, all I want you to do is type in natural log of 7. Just type that in, we already talked about that, that's the same concept when you're doing e. Natural log 7, type in your number. 1.945.
10 6 ways.
No.
It's supposed to be closed.
Type in the right number.
I did. I already got my answer. I read it out to the whole
You're
class.
going way too fast there.
E to the 1.95. No.
What? That gives you pretty much the right answer.
I'm so confused.
I already found it.
Natural log is not.
Natural log of 7.
I think I
And then that gives me that, and then I'll plug it back in.
Okay, here.
Look at that.
That's literally it. My eyes are different.
Oh, really?
Mr. Warden.
He was just looking at
You know what I think?
1.9. That actually worked then. Because that's what he always does.
the first time.
1.9.
The sine
Four,
of 6.
5, 9, 1, 0, 1, 4,
Then inverse tangent of 9,620.
Okay. Hey, do you get it?
Yeah.
Okay. Now, that's natural logs. Now, the big thing here is that there is properties to logarithms.
Kate Ford, Andrew Kiff, and Fred Burnett, please come to the office.
Alright. Hey. Basic properties here that you need to know that we covered in pre-calc, but we're going to be using the next couple times here. If you have a log of a number, you can separate them into other numbers that multiply together. Like 20 is 4 times 5. You can separate, or it could be 10 times 2. But why this could be important is anytime you're multiplying on the inside of a logarithm, you can separate it into their own separate logs.
2 is 2 by 2.
You can separate them into their own separate logs, and you can add them together. Notice this first property. This is called the product rule. You need to have that written down. That's the product rule.
Product.
That you can separate if there's two numbers being multiplied or numbers and variables, separate into their own logarithms. Now, again, coming back to the idea of math placement test. On a logarithm, maybe on the test, they ask you to find log of 20 without a calculator. But up in the instructions, they have kind of an answer key, where up in the answer key, sometimes they have the log of 4 is a certain number, and log of 5 is a certain number. No, they have these numbers. Okay,
Are we going to do something like that?
are we?
Are you going to give us an answer key sheet?
Maybe.
No.
Maybe.
I don't think you will.
Maybe. But it won't be this chapter. What do we actually have to use it? What?
That's inappropriate.
Okay.
That dialogue on your.
Hey, does everyone have the product rule?
Yes.
Okay, quotient rule.
It's subtracting.
No, it's not. Okay, quotient rule. Here we go.
Hacking is illegal.
Quotient rule. Log. Let's go 40 divided by 2. 40 divided by 2. This is log of the top. And we're going to subtract log of the bottom. So maybe that's the steps we have. So write those down. We can even go further than that.
How come rule isn't spelled ROOL? There was a law problem on the Canadian edition.
Okay, alright, so there's the basic rules. Now, the other property that you need to know, we're gonna get to more tomorrow. The other property I want you to know today is the power rule. We've actually used this one earlier. The power rule is when they have a logarithm of, let's say, 10 to the second. Oh, let's not use 10, let's go like 5 to the second. And we're gonna drop the 2 out front.
Okay.
So you can drop the power if there's some power on the logarithm. Stop. Okay. Questions on power rule, quotient rule, or product rule? We have a couple other properties we're going to cover tomorrow. These are just the basic rules, what you're allowed to do, how you're allowed to separate things. Okay, next thing. I'm trying to cover kind of just a range of topics before tomorrow.
What's tomorrow?
It's like, huh?
Pop quiz.
Is there gonna be a pop quiz?
So,
There is.
alright.
It was last year and it just wasn't great. Pop like a cola, like a
Don't say that.
Okay, hey, so, next thing. Let's talk about annual versus continual growth. Alright,
No balls.
You're right on that one.
hey, continual growth. If you have a problem that says continually exponentially growing, continual growth is written like this. Total amounts, e to the RT. This is the formula for continual growth. So if it's growing, let's say, by 3.5%, what they would do is whatever your initial amount, your initial population is, e, if it's growing by 3.5%, this is what it would look like. That's continual growth over, its lifespan. It could be decay by putting a negative on that. But how this is different, if it's annual growth, like maybe they say, hey, the population is growing this year consistently by 4%. So it's annual growth. Okay, annual growth is where we have to use this formula. Alright, so what this number is, and I'm going to put this as population amount, what this stands for is an annual growth. We don't use the natural number e. The A number, watch you. The annual growth number is, let's say we're going up by 4% all year. So this is what it would look like. We went up by 4%, and this is growth for this year. Notice we're not using an E. There's a difference there, and we never really discussed, we just talked about that there's 2 formulas for growth and decay, and we talked about the differences, but we never talked about when you use it. This section tries to pinpoint why you choose this form with like A to the T versus E to the T when it's continual growth over its entire life, not just 1 year's growth. Okay, do we see the difference in why we choose one versus the other? We just never really talked about that yet. I thought it was kind of important that we do that. They'll still give you the same number, which is kind of crazy, that you can actually use one interchangeably. As long as you're not going too far out, you can still get there. Alright, now, the last example I want to cover today. Now, I want to cover kind of one problem that we didn't see yesterday,
Yesterday was Sunday.
or Friday, that we didn't cover Friday, but I want to make sure that you know what it is, how does it look. Alright, so, here we go. Alright, and this is one problem. It doesn't have a set number for its answer, so I'm not looking for like a digit like 1.6. I'm looking for how do we solve and rearrange an equation down. So, here we go. Alright, f of x equals p 1.07 to the t. Okay. Let's say that this is my problem, and let's say the initial amount of people
Is a million.
20.
Let's go 20. Let's
20 million or just
Alright,
20 people?
we'll say it's in million.
What?
Okay, so 20 million. We'll say that's my initial population. What this function will give me is the amount of people in the very end after a certain time frame, correct?
Yeah.
And this would be 1 year's growth by 7%, you know, that's annual growth.
Taxes.
Now, here's the idea. What the book asks for, it asks for to solve this equation for t. So basically, we're rearranging the entire problem for the t variable. Okay? And I want to show you how you can approach this problem 2 different ways. This is my last problem of the day. I just want to show you 2 different ways to do it. That's it.
Do the easiest one first.
What?
Do the hard one.
I'm gonna just do the way that I would approach it.
Oh.
Okay.
Okay? Because this is
Show us how to do it?
yeah, I'm gonna show you the approach I would take because it's quick.
10 cents.
I'll show you the real way that the book would show you,
Oh, don't do that.
but it's using the same concepts. It's the same answer. The answer will look the same in the end. It's just how you get there.
We just need to throw away work.
All right. So how I would do this, I would take the logarithm of both sides, right? Because I need to get the t. What it wants you to do is solve for t. So we're basically rearranging, right?
Yes.
Hey, can we stop talking, please?
Ah.
All right. So we're gonna solve for t. So I'm gonna take the logarithm of both sides. So the log of a equals the log of, what we had 21.07 t. Agreed?
Yes.
Okay, so how I would do this, when I take the log of both sides to solve for t, drop the t, but what I'm going to do first is I'm going to separate these into their own logarithms. That's why I showed you the properties a little bit ago. This is a product rule, correct?
Yes.
They're being multiplied together. I would personally do this. Separate these into their own logs. So log 20 plus log of 1.07 t. I think this is a lot easier than what the book would show. And dropping the t and going from there, it's a pain.
It's just.
The reason why I would do this is because the only time you should drop the t out front is when you get it by itself and there's nothing like being multiplied onto it. So you actually have to separate before you drop the t. Okay, this is my rule how I would do this. So I'm going to drop the t out front of that one item. So this is going to be t log 1.07, this little plus sign, log 20, log of a. And now what they want us to do is solve for the t, get the t by itself. So solving this, I'm going to have to subtract the log 20 to the other side.
You're going a little fast.
No, I think you're going perfect.
Okay, yep, go ahead.
Are you sure?
Yeah, I just couldn't see it.
Oh, okay. If you need to scoot closer, there's a spot. Alright,
No, you're
So-
sitting in the way.
Just go see it.
we're going to subtract the log 20 over, because I want to get the t by itself. So I'm going to subtract the log 20 over. And the t, I'm going to leave it alone, log 1.07. So the t is being multiplied on the log here. That is a multiply. And now the last step I would do is I would divide that log of 1.07 over. So if you divide it over, this comes over to the other side. You could write it like this, log of a minus log of 20. And we're dividing all by log of 1.07. And you could technically separate the log of 1.07, like put it under both fractions. Like you can make each item, separate the minus sign in the middle. I would stop there, that you solve for t. But if you ever wanted to separate, it's called the law of division, that you could actually separate and put the log under each one. And just separate it like this. The reason why I would do that is that if you choose to do this, is because now one of these will just be a number and you can kind of simplify as much as you can. I like that process. That's the way I would approach that problem. I think it's a lot easier to look at. It's quick to get the t by itself. The other way to do this problem is to divide the 20 over first. So now I'm going to show you. So I'm going to show you I'm going to show you the second method, how the book would show this. I don't know which one you like, that's why I'm showing you both. Maybe you don't like my method.
I do.
Which
Do we
is
have
fine.
to separate it though? Like, I feel like we should just
No,
leave it as one.
I would have stopped at the blackboard.
Did you
Right.
But the book shows them separate.
Is there patents on this method?
No. Now,
Is it patented?
now, the book does this. They would divide 20 over first, a divided by 20 equals 1.07 with the t on it. And then they're going to take the log of both sides. So it's kind of the same concept, but just a little bit different, especially the look. Log of a divided by 20, log of 1.07 t. And they drop the t out front. They drop the t out front. And so it's log a divided by 20, and that's in a parenthesis, right? T log 1.07. And then they would divide the log of 1.07 over. And you'll probably think, like, it doesn't even look like my answer. So they're going to divide this over to get t by itself.
That's a good call.
Log a over 20 and divide by log of 1.07. Now, the reason why it doesn't look like mine is because they changed this problem. It's a quotient rule. They change it back into subtraction. Because they have two items being divided inside the logarithm. So you're allowed to separate these into what I have over there and into mine.
You have to separate them?
Yeah, they want you to separate because they explicitly say in the directions, write all of your functions in terms of logarithms without quotients. Like without quotients. So that means you can't have things being divided or multiplied inside the radical or inside the logarithm. Alright, so that's it for now. We're done.
Cool.
So.
Jimmy, where should I go?
Right
there.
Are we